Welcome! In this video, I'll show you how to solve problem 8.11 as it appears in the third edition of Griffiths Introduction to Quantum Mechanics. Now, this problem states the following. It says, use the WKB approximation to find the allowed energies of the general power law potential, which is basically some constant alpha times the absolute value of x to the power nu, where nu is a positive number. And then we wish to check the result for the case where nu is equal to 2. And well, this is the answer that we should get. So how do we approach this? Well, let's look at what this potential looks like, because when we learned about the WKB potential, what we had to do depended on what the potential looked like, right? We had different situations when there was one infinite wall, when we had two infinite walls, and when there was no wall at all. So in this case, we have this just general polynomial, but it is inside of this absolute value. And that means that this will be an even function always. It doesn't matter what nu is, it's going to be an even function. And that's going to be very important. Also, we must understand the way that polynomials work, right? So polynomials are usually something like this, maybe, right? In the case of x squared, or maybe something with a few more of those, right? There's going to be quite a few intersections, but it's always going to be just sloping. There's not going to be any sort of infinite wall. So for that reason, what we have to do is use the result that we have already derived, which is this thing right here. This is basically the formula that we got in the case where we have no sloping walls, or basically only sloping walls and no infinite walls. That's what I meant to say. And what we have to do is simply plug in the value of the momentum and solve the integral. That is what the WKB formulation leads up to. We had to do some very nasty derivations, but now we have our results, and all we have to do is plug it in. We don't need to solve the Schrödinger equation, none of that. So let's see. Let's plug in the momentum here. What is the momentum? Just a quick reminder. So the momentum, it is the square root of 2m e minus the potential, but in this case the potential is alpha absolute value of x to the nu power. So let's plug it in. So we are integrating from x1. What is x1? x1 is one of the turning points. Now, we don't really know what the power of nu is in this scenario, but let me draw this, let's say, for the case where nu is equal to 2, right? We have this just normal parabola. So in this case, this is our potential, and our particle or our system, whatever it is, it will have some energy E. And we have 2 points where the energy and the potential are equal. One of them is at x1 and one of them is at x2. Okay, so that is what x1 and x2 are. Those are the classical turning points. Keep in mind, this is a semi-classical approximation, so that's also why we use this semi-classical approach to momentum. Okay, now let's plug the momentum in. So 2m e minus alpha times the absolute value of nu, and we take the square root and dx. Okay, and this of course has to be equal to this thing here, but let's first work out this integral and then we will set it equal. Now, how can we work around this integral? Well, we have to get rid of the absolute value first, right? Integrating the absolute value is kind of gnarly, so maybe let's try to avoid it. Now, what else could we do? Well, take a look at this situation. We are in this system where things are symmetric, okay? Because of the fact that we have the absolute value, it's making things symmetric around the x, basically x equals 0, right? The y-axis. So that means that x1 is basically minus x2. So we can just go ahead and plug in for any of those. It doesn't matter which one. Let's say x1 is minus x2. You could substitute whatever you want. So minus x2 to x2. So now we have this. But notice that it is an even potential, as we said. So going from minus x2 to x2 is the same as going from 0 to x2 twice. So we can make our integral much nicer, and by doing that, we get rid of the absolute value right? We have already taken into consideration, because what we are going to be summing over is the area under the curve, basically, right? And it is the same to the right side and to the left side. So we might as well just integrate here and multiply by 2. So that's basically what we're doing. It's the normal strategy whenever we're dealing with integrals that have an absolute value. Okay, so now we wish to make notation a little bit simpler here. So let's factor out some of our constants. So for example, we can factor out, well, the 2 is already outside, but we can factor out 2me. It doesn't really matter if you do this or not. In the end, these are simply constants. If you can simplify notation, it will make calculations less annoying. But in principle, it doesn't really change much. So this here gives us 1. And then we have minus alpha divided by e times x to the new power. And then, of course, dx. Now, let's see. Notice that x2, of course, is something that we can easily determine because it is a turning point. And what is a turning point? It is the point where the energy is the same as the potential. So the potential evaluated at x2 has to be equal to the energy by definition, right? Otherwise, it wouldn't be x2. And the potential is alpha absolute value of x2 to the new power. And well, x2 is, of course, already positive, so we don't really need to have the absolute value there at all. But how can we actually solve this integral? So the way that it stands, it's very difficult, if not impossible, because we don't really know what the value of nu is. So we would have to find some formula that gives us some sort of general result in terms of nu. Fortunately for us, that already exists. So you might want to just look up an integral table, but I will walk you through how to do it. Now, there exists a function which is called the beta function, which actually looks relatively similar to what we have here. And what we wish to do is transform this into something that resembles it. So the beta function, which will help us solve this, is a well-studied function, which is of the form 0 to 1. I'm going to use other names for the variables, just to have this in general. So this is t to the x minus 1 power, 1 minus t to the y minus 1 power, dt. So this function will help us find the answer, because we can express this function as the product of the gamma function of x times the gamma function of y divided by the gamma function of x plus y. So that is the reason why we wish to transform this integral to this form. Now, of course, if you have never heard of this, you're not going to be able to come up with it, but it's all right. The first time, it's very, very, very normal to not think of it. Okay, so how do we transform it? Well, let's begin noticing that we wish to go to something of the form 1 minus t, but we have 1 minus alpha e blah blah blah. So maybe let's not use the same name t, let's call it z or something. It doesn't really matter, to be honest. Let's say that our new variable z will be alpha over e times x to the new. And now let's find x, because of course we will need to plug it back in when we find dx, right? We wish dx, and we need to find dx to plug it in. So from here we see that e times z over alpha, this is x to the new, so we can take the nth square root and we find x. So from there, of course, dx is simply, let's see, e and alpha, I'm gonna put them aside because they are constants. And then we have z, so we take the derivative, we get 1 over nu times z to the 1 over nu minus 1 power dz. So let's plug all of this into our former expression. So this thing right there, right? So we get that 2 square root of 2me integral from, okay, we need to find the new limits of integration. So that's easy. We simply plug in the old limits in our new variable. So when x used to be equal to 0, now we get, well, 0 again. And when x used to be equal to x2, now we get, let's see, z2, perhaps, let's call it that way. This is equal to alpha over e x2 to the new power. Now, this doesn't look good, but let's look at what we found before, because we saw that the energy is equal to alpha x2 to the new power. Or, written another way, if I divide by e, 1 is equal to alpha over e to the x2 to the new power, which is precisely the upper limit of integration. So that means that our new limits of integration are 0 and 1. So we can see that with this change of variable, we're doing pretty good. Okay, what comes next? Well, now let's just plug everything in. So we get the square root, which I will write as 1 minus this z to the 1/2 power, and then dx, which we know is e over alpha 1 over nu times 1 over nu, and then times z 1 over nu minus 1 dz. Okay, so there's a few constants that we don't need. So 2e, let's take out e over alpha to the 1 over nu. Then all of this is divided by nu, and I think that's all of our constants. And then we have integral from 0 to 1, and what else do we have? Then we have 1 minus z, and I'm going to write this differently, not as 1/2, but as 3/2 minus 1, just to make sure that this resembles our other notation. Then we have z to the 1 over nu minus 1, that doesn't need any changing. Now, compare these two expressions. We have 1 minus z, 1 minus t, 3/2 minus 1, y minus 1. So basically, these things are the same with y equal to 3/2, and we also have z to the 1 over nu minus 1 and t to the x minus 1. So x is 1 over nu. So this expression is the beta function of 1 nu over nu and 3/2. So let me write it like this. So 2 times the square root of 2me over nu times e over alpha 1 over nu, and then we have the beta function of 1 over nu and 3/2. And what is that? Well, we already know, right? This thing right there. So 2me over nu, and well, the constants, they haven't changed. So 1 over nu. And now we write the result. So gamma of 1 over nu, gamma of 3/2, and then we have gamma of 1 over nu plus 3/2. In principle, this is already the answer, but it isn't really what we are looking for. Now, what we want to do is find the energy, so of course we still have to plug this back in here, but there's still a lot that doesn't quite look like what we want, right? So first of all, let's remember that this is equal to n minus 1/2 pi h bar. All that we were doing was simply solving this integral. That's all we have been doing this entire time. So now our mission is to somehow simplify all of this. So something we can do is, first of all, take a look at this part right there. So there is an important property that we must remember, and it is that the gamma function of x plus 1, x in general, of course, not really related to the x and the beta function, this is equal to x times the gamma function of x. So in this case, if you write this gamma function as gamma of 3/2, or rather 1/2 plus 1, this is equal to x, which in this case is 1/2, times the gamma function of x, which again is 1/2. Now the gamma function of 1/2, this is the square root of pi. That is a well-known result. So we can rewrite this part as simply the square root of pi over 2. So this 1/2 here will cancel out this other one there. And let me write this a little bit larger. So square root of pi. So there we go. We simplified this a little bit. Now what we need to do is we wish to find the energy. How can we possibly find the energy here? Well, we need to just put every energy term together and then divide by everything else to isolate the E in this equation. So let's begin by doing that. So here we have E to the 1 over nu plus 1/2. And then we have everything else. So perhaps let's just divide by everything else, beginning with n minus 1/2. This is still on the other side, so pi h bar. And then we have everything else. So we have to multiply by gamma of 1 over nu plus 3/2 divided by gamma of 1 over nu. And then we have this square root of pi down here. Then we need to multiply by alpha to the 1 over nu. And what else do we have? Then we have to multiply by nu as well. So nu is somewhere over there. And we still need to divide by the square root of 2m. I believe that is everything. Okay, so finally, we need to take the square root of this. How do we do that? Well, let's take common denominator. So this is basically 2 plus nu divided by 2 nu. So taking common denominator, we get 2 plus nu divided by 2 nu. So basically, we need to raise everything to the power of the inverse of that. So basically, E will be everything in here, n minus 1/2 times pi h bar. We don't really need this other parentheses. So gamma of 1 over nu plus 3/2 divided by gamma of 1 over nu. And let's put every square root together. Actually, we can cancel out the pi's, I guess. So I'll put the square roots here. So we get square root of pi divided by 2m. And what else do we have? We still have this nu, so we will put it there. Let's see, I used this. We are still missing the alphas. Okay, so then we have alpha to the 1 over nu, and all of this is raised to the 2 nu over 2 plus nu. There we go. So in principle, this is already correct. And maybe let's compare with our original with the assignment here. So we have n minus 1/2 there. So we have this, we have the h bar, we have this square root of pi divided by 2m. This alpha is different. We still have this, we have this gamma there. This gamma is different. They don't have this nu flying around, and the exponent is the same. So we have to do a little bit of algebra to get to the exact same form. Honestly, it doesn't really matter too much, but let's do it anyways. So what do we do about this nu? Well, again, let's keep in mind the expression, the property of the gamma functions, that gamma of x plus 1 is x times gamma of x. So we can write this gamma down here as 1 over nu, right? Because 1 over nu is nu, so we haven't done anything illegal. And here we have basically this. We have x, which is 1 over nu, times gamma of x, gamma of 1 over nu. So this thing right there is gamma of 1 over nu plus 1. Okay, so now we have the gamma function sorted out. The only thing that is different is this alpha here. So they want to write it inside of the square root. So something we can do, I guess, is just multiply and divide by alpha to the 1/2. So alpha to the 1/2 divided by alpha to the 1/2. And this we simply put inside of the square root. So we simply push this one into the square root, so 2m alpha. And then here we have alpha to the 1 over nu plus 1/2. Okay. And we now take this alpha out of our parentheses. Okay, so we take this outside and we get that alpha to the, it was 1/2 plus 1 over nu. This is raised to the power 2 over nu, 2 plus nu. But these two things will cancel out because 1/2 plus 1 nu is precisely the thing that we had before. So if we take common denominator here, we get 2 plus nu divided by 2 nu. So 2 plus nu divided by 2 nu. These are multiplying, by the way. So the exponents cancel out, and we simply get alpha, which will multiply here in the front, and we get exactly what we wanted to find. So this is our result. These are the energy levels, sub n, of course, precisely as we wanted. Now, the other part of the problem, they ask us to check the result for the case where nu is equal to 2. So let's see what happens there. So if nu is equal to 2, so basically when we have alpha times the absolute value of x squared. Okay, in this case, we don't really need the absolute value, to be honest, right? It's going to be positive either way, but regardless, here we have En, this will be alpha to the n minus 1/2, and then we have h bar and gamma of 1/2 plus 3/2, which is 4/2, which is 2. And here we have 1/2 plus 1, which is 3/2. But we already know what gamma of 3/2 is. This is, right, this thing is 1/2 gamma of 1/2, which is square root of pi. All right, so this thing here is 1/2 times the square root of, I don't know why I wrote that, times the square root of pi. And gamma of 2, that is, just to show you, gamma of 2, this is 1 times gamma of 1, which is 1. So this thing here is simply 1, so 1. And then we have times the square root of pi divided by 2m alpha. And all of this is raised to the 4 divided by 4 power. So simply 1. Okay. So now the square roots cancel out. This cancels out with this. And this 1/2 we can write as 2 up there. So this is basically 2. And since there's a square root of 2 here, we can write it as square root of 2. Anything else? I don't think so. So now let's put everything together. So we have n minus 1/2 times h bar times alpha square root of 2. Actually, this alpha can contract with this thing there. So we get square root of alpha 2. And also we have an m. So let's include it in the square root. So alpha times 2 divided by m. So we included this, 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 and this. There we go. Now, what does this look like? These energy levels, what do they look like? This kind of looks like a harmonic oscillator, right? The energy levels for the harmonic oscillator with n equal to 1, 2, 3, etc. But in the case where our omega is precisely the square root of 2 alpha over m. And in that case, we get En is n minus 1/2 h bar omega, which is precisely the energy levels of this harmonic oscillator. So we can see that this is precisely that case. So it's a very, very interesting result to find. And in fact, we can corroborate that because from here, we can see that we can square this. So we get omega squared times m divided by 2. This is equal to alpha, right? We can find what alpha is. And if we plug this into our potential, we get that the potential is alpha times x squared, but alpha is 1/2 m omega squared x squared, which of course is precisely the potential for the harmonic oscillator, which makes sense. I mean, it has to be since we found the energy levels of the harmonic oscillator. So there we go. That's the solution to this problem. As you can see, all we did was just solve this integral, which was the difficult part of the problem. And other than that, it was just some simple algebra to find our result. And that is the beauty of the WKB approximation. It turns very difficult problems of solving the Schrödinger equation into simply solving one integral. And sure, it can be annoying, but it's a lot easier. So I hope this video was useful to you. If it was, please consider leaving a like on the video, commenting and subscribing, and maybe even checking out my Patreon. So I'll see you in the next video. Thank you very much for watching.